All right. Welcome everyone to the, is this the 58th? Yeah, to the 58th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Francesca Fedele from the University of Leeds, and she'll be talking to us about Ext-projectives in subcategories of triangulated categories.
Thank you very much for the invitation and for the opportunity to talk in this very nice seminar. I'm very sorry about the technical problems. Hopefully this is well enough. I was planning to actually add a few notes to these written notes, so hopefully this works fine enough. I don't know, is there a way to, maybe just, no, okay, fine. Okay, so I wanted to talk about Ext-projectives in subcategories of triangulated categories. And so just as a starting point, I wanted to give a very brief introduction about Auslander-Reiten theory, just to see in what areas it has been developed, because it's the setting where my results take place. Just as an initial thing, the Auslander-Reiten theory was first introduced by Auslander-Reiten in the 70s in a series of papers, and it started with for finite dimensional algebras or for some special algebras, and it was used to study the module category over there. Can you actually see my pointer as well, or maybe not? So about module categories over there. So it's the study of these special short exact sequences that in some way collect the important information about the building blocks of the objects, which are the indecomposable modules, and the building blocks of the morphisms, which are the irreducible morphisms. And studying this set of sequences, then you can recover most information that's needed for these module categories. And since it gives you all this relevant information, then it was used, it was generalized to more general categories, and because it's also used to give relevant information in other categories. So it was first generalized to more general Abelian categories by Auslander-Reiten in 75, then to some of their subcategories, some special subcategories by Auslander and Malo. Then more work was done about subcategories of these module categories, mainly by Kleiner. And then all of this theory was also developed into the triangulated analog, first by Appel in 88, and then in the study in their special subcategories by Jorgensen in 2009, and we'll say a bit more about these. And these results by Jorgensen actually are the sum of the triangulated analogs of the results by Kleiner. So my project was mainly to give more information about Kleiner's results in the triangulated analog. And then Auslander-Reiten theory has actually been extended to by many more people and in more generalization. So for example, I've also studied Auslander-Reiten theory in higher homological algebra, but it's not the focus of today's talk. So, oh, actually putting two pages together, okay. So let's look at the setup from today. I'm going to use a nice triangulated category, T, with some shift functor, which I denote by sigma. And then this is a skeletally small k-linear for some field k home-finite triangulated category with split idempotent. And all of these nice properties make it a Krull-Schmidt category. Then T, we also assume that T has a self functor, which is this special functor from S to itself, which basically the idea of a self functor is that, well, here I would have written it down, but actually maybe, yeah, it tells you that the home space between two objects X and Y is isomorphic to taking the standard duality and compositing it with the home space of Y, comma, the self functor applied to X. And actually, maybe I can, do I have it? Okay, never mind. Okay, so this is a special functor that the reason why we assume it, we have it is because then we can we can assume there are the Auslander-Reiten triangles. So if you have a Serre functor, you also have these Auslander-Reiten triangles. And Auslander-Reiten triangles are these special triangles that are as close as possible to split triangles without actually splitting. So in here, a non-splitting triangle would be one where the third map here, the one from T to sigma x, is non-zero. But then we have the factoring property that, again, I would written it down. But if you have a map from X to some other object in your subcategory, in your category, which is not a split monic, then this map is forced to factor through this map from X to Y, so through the first map in your triangle, and that's why we call this map left almost split. And then similarly, there is a dual notion for the object ending at T. So the morphism ending at T, there are not split epimorphism. These factor through Y. And this is why we call the second map a right almost split morphism. The existence of the Serre functor is important because then if you take any indecomposable T, you're guaranteed to have such an Auslander-Reiten triangle ending at your indecomposable. And then you can also say what the other end object, what I called X here is. And this is actually obtained by taking the Serre functor, composing it with the shift, the inverse of the shift, and applying it to T. And then we get our X. So if you have a Serre functor and a nice enough triangulated category, you always have these Auslander-Reiten triangles. And then the last thing we assume in this setup is that we also fix an additive subcategory, and by additive I mean full closed under isomorphism under direct sums and direct summands, and which is also closed under extensions. And these are very important and special subcategories. So closure under extension means that if you have a triangle where the first and the third objects are in your subcategory, then the middle object is also forced to be in your subcategory. So for example, here, this A to B to C to sigma A, if you know that A and C are in your subcategory, then B is forced to be in your subcategory. And I just want to point out that we're not assuming our subcategory is closed under shift or the inverse of the shift. So actually, sigma A could be outside our subcategory. It could be in, but it could also fall outside. So if we also had closure under the shift, we would have a triangulated subcategory, but we don't need our subcategory to be that strong. So then you can, as I was saying, extend Auslander-Reiten theory in subcategories which are closed under extensions. So in this kind of subcategories. And an Auslander-Reiten triangle in C is a triangle in the ambient category T, where the first and the third object are in your subcategory. And then in this case, of course, the middle one B also needs to be, because you assumed it's closed under extensions. And then we have the factoring properties I was talking about. So this left almost split and right almost split property. They're still true, but only when your morphism ends in objects in your subcategory. So for example, here, if you had a morphism from A to some other object in C, so in the subcategory, which is not a split mono, then this would factor through the morphism from A to B. And similarly, a dual notion for the second morphism. And again, these are non-split triangles. So the third morphism, the one from C to sigma A, is non-zero. So the first question one could ask is, when do we actually get such triangles in the subcategory? And Jorgensen in 2009 replied to this question, basically. And this is actually a triangulated version of a result by Kleiner from '97. I was mentioning this paper earlier. So if you have an indecomposable, and both Auslander-Reiten triangles in subcategories and Auslander-Reiten triangles in the ambient category, they need to start and end at indecomposable. This is not part of the definition, but it can be proven that if you have such a triangle, it needs to start and end at indecomposable. So if you have an indecomposable in C with this non-vanishing property of X, then there is an Auslander-Reiten triangle in the subcategory C, ending at C, if and only if there exists a cover of this object as composed with sigma inverse of C. And so if you know you have covers for some reason, then you would always get, you would always be able to build an Auslander-Reiten triangle in your subcategory as long as you have this non-vanishing condition. And X groups in triangulated categories are nothing more than Hom spaces. So actually X1 of C comma something else is actually the same as Hom of C comma sigma applied to this other object. So we're basically saying that there exists a non-zero morphism from C to sigma of something in your subcategory, so that we're guaranteed that we can build a non-split triangle, because of course, otherwise we would have a problem, because we want our Auslander-Reiten triangles not to be split. So this was the result by Jorgensen, and this object here, as composed with sigma inverse of C, is actually the other end term of the Auslander-Reiten triangle in the big category T. So we're actually, what we're doing, we're approximating the other end term, this S composed with sigma inverse of C, with some object in A. Covers are nothing more than that. They're just approximations of some objects in the ambient category with some objects in your subcategory. And then we're completing it to a triangle, which then ends up being an Auslander-Reiten triangle in our subcategory. So this was the result by Jorgensen. And what I was focusing more is the other set of objects. So these objects that do not have this non-vanishing property. So if you actually take an indecomposable C, where X1 of C comma anything in your subcategory is 0, then you know for sure there is not an Auslander-Reiten triangle in C which ends at this object, because if you look at any triangle of the form A to B to C to sigma of A, where A is also an object in C, then having X1 C comma this comma the subcategory equal to 0 means that Hom of C comma sigma applied to anything in your subcategory is 0, and more specifically the morphism from C to sigma of A ends up being 0, and your triangle ends up splitting. So it's not an Auslander-Reiten triangle in the subcategory. We call these objects Ext-projectives in subcategory. So they're always Ext-projective with respect to a specific subcategory. And the reason why they're called this way is because they behave like projective objects in module categories, for example. Because, well, projective objects in module categories are exactly those that, such that whenever you have a short exact sequence ending at them, that short exact sequence splits. And these objects are exactly those for which whenever you have triangle in your subcategory ending at them, this triangle is forced to split. So we cannot have an Auslander-Reiten triangle in the subcategory ending at an Ext-projective, but instead we can often build something similar. And these are what we will be calling left-weak Auslander-Reiten triangles in C. So let's take an indecomposable module C, which is Ext-projective. And let's assume for some reason that we know that there is a minimal right almost split morphism in my subcategory C. Now, this seems a very strong thing to ask, but actually, if, for example, you know that your subcategory is functorily finite, you know for sure such a thing exists. So if you're looking at a functorily finite subcategory, then you're safe. Even more specifically, if you're looking at something with finitely many indecomposables, which a lot of the examples I've been looking at are, then you have functorily finiteness for free, and so you also have minimality, the existence of a minimal right almost split morphism in your subcategory for free. So let's say that we know such a thing exists, then we can build what we call a left-weak Auslander-Reiten triangle in C. So we actually take this minimal right almost split morphism in C, B to C, this beta here, And then we extend it to a triangle. You can always expand a morphism to a triangle in a triangulated category. This triangle will not be split because you've taken B to C to be right almost split, which forces your triangle not to split. So your gamma here is a non-zero. And then when you complete it to a triangle, you know for sure that X falls outside your subcategory. And that's because otherwise your triangle would split, as we just explained before. So X is outside your subcategory, but we can check that actually X is still an indecomposable module. It's not in our subcategory. And psi is a C envelope of X, which means it's a left minimal approximation. So actually, if you have any object, any morphism from X to something in your subcategory, then these need to factor to psi. So you actually end up having a very similar property to the factoring property of an Auslander-Reiten triangle in the subcategory, but the only difference is that your initial object X is not in the subcategory. And moreover, you also have that the object X and C are two indecomposable objects which determine each other, just like happens for Auslander-Reiten triangles. So for Auslander-Reiten triangles, when you have an indecomposable, you can always determine uniquely the other end term of your Auslander-Reiten triangle. And here we have a similar property. Of course, it's still fairly different from an Auslander-Reiten triangle because it's not, the first object is not in your subcategory. So we call it a left weak Auslander-Reiten triangle because it has this weakness on the left object. And of course, you can also have the whole dual result for right weak Auslander-Reiten triangles if you try to start at a given indecomposable, which will be Ext-injective instead of Ext-projective. So these triangles are very interesting, and they still give us some more information about our subcategory. And another important thing they do is that sometimes they can be used to build a new extension closed subcategory starting from the initial one we were looking at. So extension closed subcategories are very deeply studied, and they're very important subcategories. So if we find a way to find new ones, it's always good. So let's see when we can actually do something like that. And this process will actually end up being similar and sometimes coincide with the classic notion of mutation, as we will see. So let's start with just some notation. If X is an additive subcategory of T, then we call P of X the set of all the Ext-projectives in X. So the way I described them before, it's all the objects in X in this subcategory, such that X1 of these objects, comma, anything in the subcategory is 0. And dually, you can describe Ext-injectives, which I will call I of X. And these are the set of objects such that X1 of anything in your category, comma, these objects is 0. So you swap the role of the object and the rest of the category here. So we still assume C is a subcategory, which is additive and extension closed. And let me also assume it's functorially finite. The next result and the subsequent ones could be stated in a slightly more general way if you don't assume functorially finiteness, but then you have to be more careful about some extra assumptions and it becomes a bit more complicated. So just for the purpose of this talk, I'll just assume it's functorially finite. Then if we take an indecomposable in our an indecomposable Ext-projective in our subcategory C, so this object C, we know there exists a left weak Auslander-Reiten triangle in C, just because we are in the functorially finiteness, we have assumed functorially finiteness, so we know such a triangle exists. And then we build this C tilde to be another subcategory inside our C. And this is the additive subcategory obtained by looking at all the indecomposables in your C and kicking out the indecomposable C we were studying here. So we kick out this Ext-projective indecomposable, And then we look at the additive subcategory that's generated by the rest of the indecomposable. Then you can build C prime to be actually obtained by taking C tilde, adding the indecomposable X, and then looking at the additive category we obtain this way. So just as a recap, if you want to go from C to C prime, you look at all the indecomposables, you take out C, so this Ext-projective we're looking at, and you replace it with X. And then you look at the new additive subcategory. So you mutate your subcategory in some sense, even if this is not the classic notion of mutation. Then these 3 points, A, B, and C, describe, in some sense, tell us something more about when this new subcategory is closed under extensions. So if you know that your X is both Ext-projective and Ext-injective in the new subcategory C prime, then you know for sure that C prime is closed under extension. And on the other hand, B and C, in some sense, you can think of them as an attempt of a converse, even if it's not a full converse. So if you also know that the endomorphism ring of X and the one of C are one-dimensional over your ground field, and if you know that C prime is closed under extension, then X is for sure an Ext-projective, Ext-injective in your C prime. And similarly in C, if you know that the endomorphism ring of C is one-dimensional over the ground field, C prime is closed under extension, and X is Ext-projective in this new category, then X is also Ext-injective. So let's look at a special case where everything becomes a bit more nice to look at. So let's now assume that T is Tucalabi-Yau. And Tucalabi-Yau means that not only you have a Serre functor S, but you actually know that the Serre functor is sigma squared. And there are a lot of interesting triangulated categories where this is true. For example, the one you probably have heard a lot about is our cluster categories of various types. And then the interesting thing is that if your T is Tucalabi-Yau, then if you apply the definition of a Serre functor, where with this specific notion where S is sigma squared, then you end up saying that X1 of XY is isomorphic to the standard duality composed with X1 of YX. But this just means that the Ext-injectives and the Ext-projectives coincide if your T is Tucalabi-Yau. So if your T is Tucalabi-Yau, Ext-projective objects are the same as Ext-injective objects, and this is true for any additive subcategory of T. Then a corollary of the theorem says that if T is Tucalabi-Yau, and you also know this extra property that the endomorphism rings of X and C are one-dimensional over the ground field, then C prime is closed under extension if and only if X is Ext-projective in the new subcategory, which also means X is Ext-injective in the new subcategory, because as I just said, Ext-projective and Ext-injective coincide in this case. But yeah, this endomorphism ring condition is still important. So as I was mentioning before, this is a very similar process to the one of mutation of some special subcategories. So you might be familiar with mutation of like cluster tilting objects or rigid objects. Actually, Iyama-Yoshino defined a mutation of rigid objects. And I will recall what this means in a moment. But these two processes are different in general, but they do end up being the same in some special cases, which is very interesting, I think, because yeah, mutation has been widely studied and is also a way of producing a new subcategory that sometimes has most of the interesting properties of the initial subcategory you started with before mutating. So yeah, let's recall briefly what mutation, Iyama-Yoshino mutation is. So if you start with a functionally finite rigid subcategory of your C, and rigid means that home of anything in this D, comma, sigma D is equal to 0. So there is no home from an object in D to a shift of an object in D. Then if you take an object in your subcategory C, you can take a D cover of this delta because we assumed D to be functionally finite. So an approximation of your object C with some object in D, this is always possible to do. And then you can extend this delta to a triangle in your triangulated category. And this is a unique process because covers are unique up to isomorphism, and in a triangulated category, when you extend a morphism to a triangle, you can do it in a unique way up to isomorphism. So you then look at this other object mu D of C, which is called, and you call it the backward demutation of C, and this is well defined. Then the backward demutation of the whole subcategory C is denoted by mu C of D, and it's given by all of the objects of this form, so mu D of C obtained by this process, and also all of the objects in D. So you take all of the objects in your rigid subcategory and all of the objects mu D of C for any C in your C. And then this is the backward demutation of C. There is also a notion of forward demutation, which is dual to this. Then my result tells that if, let's assume now that C has finitely many indecomposables, and take an indecomposable Ext-projective in C with this extra property that the endomorphic ring of C is isomorphic to the ground field. Then, thanks to the fact that we have finitely many decomposables, we can construct a left-weak Auslander-Reiten triangle in C. And we can build C tilde and C prime just as before. So C tilde is obtained by looking at the indecomposables in C and taking out this one we're studying, C. And C prime is obtained by taking, by adding the indecomposable X to this list of indecomposables from which we have removed one. Then if we know that C is Tucala-Diao and X is Ext-projective in the new subcategory we've built, then if we mutate C, the subcategory C, with respect to the rigid subcategory obtained by, which is add of all the Ext-projective in C tilde. So where C tilde is the subcategory inside C, where we have removed the indecomposable C. So if you mutate C with respect to all of the Ext-projective in C tilde, then you obtain C prime. So in this case, mutating your C with respect to this choice of D coincides with my process of constructing this new category C prime. And if you know that your object X is Ext-projective with respect to this new subcategory, then this new subcategory we have obtained is actually closed under extensions. So this is interesting because, as I said before, our mutation, our process and the classic notion of mutation end up being exactly the same process in this case. I know this was a lot, so maybe we can look what happens in a specific class of examples to conclude the talk.
I have a question regarding this
Yes.
coincidence between Ext-projectives and Ext-injectives. So does the following question make sense? What is the largest exhaustive class of T such that we have coincidence between Ext-projectives and Ext-injectives? Like if we have that coincidence for a T, are there properties, interesting properties of T implied by that coincidence?
So you mean for T, if you choose your subcategory to be in T, to be the whole T?
Yeah.
Well, I think, in that case, you wouldn't get any Ext-projectives or Ext-injectives because Unlike for module or abelian categories, you don't have projectives in the triangulated category. So actually you can build an Auslander-Reiten triangle for any object, for any indecomposable object. So you do not have Ext-projectives for the big category. Or also, I think if you have an actual triangulated subcategory, you wouldn't get Ext-projectives. You only get them if you have these extension closed subcategories, which are not also closed under sigma or its inverse. So you really need to look at the subcategories that are not triangulated inside your triangulated category.
Right.
Does that answer your question possibly?
I'll ask a related question at the end of the talk. It's all right. Thank you.
Okay. Yeah. Sorry if I didn't. Yeah. Okay. Maybe we can talk more later. But yeah, let's look at the cluster category of thinking type A. So I chose AN with this specific orientation for some positive integer n. Then if you're not familiar with this, don't worry too much, because we'll actually look at the combinatorial model, the geometric realization. So it's not too bad. But if you are familiar with the cluster categories, so this is obtained by taking the bounded array category of mod Kn, and then you look at the orbit category obtained by taking the orbit of tau, the integer orbit of tau inverse composed with sigma, where tau, well, tau is the Auslander-Reiten translation, and tau inverse is its inverse, and it's actually obtained by composing again, this time the inverse of the Serre functor with sigma. Right, yeah, don't worry too much about the definition of this category. The only thing that's important is that it's a triangulated category that satisfies our setup. It is to Calabi-Yau, so we are in this special case where everything is nice. And then all home spaces between indecomposables are either 0 or one-dimensional over the field. So this endomorphism ring condition, we don't have to worry about that. And again, and also we have a finite number of indecomposables. So punctuality finiteness always comes for free. So it's the ideal category to work with because everything becomes nicer and easier. What's the geometric realization? So instead of looking and working with this apparently complicated category, you can look at its geometric realization. You take a regular convex n plus trigon. So for example, in the example I have here, I chose n to be 11, then you will have to get 14 gone. And then the diagonals in this polygon are in one-to-one correspondence with the indecomposables in your triangulated category, where a diagonal is a diagonal joining two vertices that are not next to each other. So like 5, 6 wouldn't be a diagonal, it's just an edge of your polygon, but 5, 7, 5, 8, 5, 9, all of these are diagonals. And then the extension closed subcategories of T are in one-to-one correspondence with Ptolemy diagrams in T, and these are collections of diagonals in your polygon, which satisfy the Ptolemy conditions. In other words, a way to describe Ptolemy diagrams, we can look at the example. You choose a set of non-crossing diagonals, like the green one in the picture, and these diagonals are allowed to have one end point in common, but they're not allowed to cross inside the polygon. So you choose a set of such diagonals, and then this divides your bigger polygon into smaller cells. So for example, here, if you look at the leftmost picture, it divides our bigger fourfingon into 5 smaller cells. And then the Ptolemy diagrams are those where you actually look at you treat all these cells as independent polygons, so they're not allowed to talk to each other anymore. And you choose whether each of these cells is an empty cell, which means we're not taking any of the diagonals in it, or it's a clique. which means we're taking all of the diagonals in it. So we're not allowed to take some of the diagonals of a cell. We either take all of them or none of them. So the extreme case, it's on the left, where we've chosen to take all of the cells to be empty. The second case is the other extreme case, where we have chosen to take all of the cells to be cliques, so all of the diagonals inside the cells, but still note that we're not allowed to cross the dissecting diagonals. So we're not allowed to take any diagonal that crosses one of the green ones. Or a less extreme case is the third one, where we've chosen 3 of the cells to be empty and 2 of them to be cliques. So we're taking all of the diagonals into the cells and none of them in the remaining 3. One more extreme case is if we started with a maximal set of dissecting diagonals. This would be a triangulation. The maximal set we can take of diagonals that do not cross each other is a triangulation of your polygon. And then this is a very special case because it then corresponds to what is called a cluster tilting object or subcategory in your triangulated category, in the cluster category. And then in that case, mutation of cluster tilting objects has been widely studied, and it does actually coincide with our process. But yeah, if we look at this more relaxed condition where we take a set of dissecting diagonals and then choose some of the cells to be cliques and some empty cells, then it's not too hard knowing the geometric model to show this proposition that an indecomposable in the corresponding subcategory to the Ptolemy diagram is Ext-projective if and only it corresponds to a dissecting diagonal. So as I said before, indecomposable corresponds to diagonals. So an indecomposable is Ext-projective if and only it is a dissecting diagonal. So again, if we look at this example on the right hand side of the slide, we have that the corresponding category C, extension closed subcategory C, would be obtained by taking add of all the indecomposable objects corresponding to the blue diagonals and to the green ones. The green ones correspond to Ext-projective objects, and the blue ones correspond to the remaining objects which are not Ext-projective. So the objects in blue will appear as endterms of Auslander-Reiten triangles in C in the more classic sense. So you can actually apply Peter Jorgensen results to these blue objects and find the Auslander-Reiten triangles in C corresponding to them, while the objects in green are the dissecting diagonals. So these are the Ext-projectives, which are also Ext-injective in this case, objects. And then these are endterms of left-weak Auslander-Reiten triangles in C. So let's look at a couple of left-weak Auslander-Reiten triangles. Again, I haven't really told you how all the morphisms and triangles are built in this model. There is a combinatorial way of building them. So it's not too difficult. It's just that because of time, it doesn't really make sense to give more details. But if you look at the dissecting diagonal 5, 8, so I've called this C in this smaller drawing, then you can complete it. Well, you can build the left-weak Auslander-Reiten triangle in C. So the 4/8 to 5/8 would be the minimal right almost split morphism ending at your dissecting diagonal. Then you complete it to this triangle and you obtain that your other endterm X is 4, 6, this diagonal in red here, which as you can see does not belong to our subcategory C prime as we expected, because this is a left-weak Auslander-Reiten triangle. And then C prime in this case would be obtained by removing C and adding X. But as you can see here, we have a problem because this X is not an Ext-projective in our new subcategory C prime because it's not a dissecting diagonal. And then the corresponding C prime is not a closed under extension subcategory, but this is exactly what we would expect, because as if you remember the result we looked at before, the C prime is extension closed if and only if this object X is an Ext-projective. And here we can see it's not an Ext-projective, so the resulting C prime is not closed under extension. On the other hand, if we chose 0, 4, so these other dissecting diagonals joining 0 and 4, there is again a rule that tells you how to construct the left weak Auslander-Reiten triangle. And we can see that the other end term is X, given by 1, 12, again in red in the picture. But then the new set of diagonals we obtained by removing C and replacing it with X is a Ptolemy diagram this time, because this X, well, it should really be in green in the second diagonal, because it's a dissecting diagonal. But then C prime obtained by this X plus the rest of green and blue diagonals in the drawing on the right is a Ptolemy diagram, and it's closed under extensions. And this is thanks to the fact that X is a dissecting diagonal in this new diagram, and hence it is an Ext-projective by the results I was talking about before. So then more generally, this procedure always works whenever you start with some C that borders to empty cells. So actually, if your dissecting diagonal you look at borders to empty cells, this process will guarantee to produce an extension closed subcategory C prime. So, and this is what this last proposition is telling us. If C is an Ext-projective indecomposable in C, and we have this corresponding left weak Auslander-Reiten triangle, then C prime is extension closed, and it's actually equal to the mutation of C with respect to the additive category obtained by taking all of the Ext-projectives in our C tilde, if and only if the corresponding diagonal C borders to empty cells in the Ptolemy diagram that corresponds to our subcategory we started with. And just as a final remark, this also agrees with mutation of cluster tilting objects, because as I said before, cluster tilting objects actually correspond to triangulation. But then if you want to mutate a triangulation at any of its diagonals, this diagonal borders two triangles, and two triangles are always two empty cells. So you can always remove one and replace it with the only other option available. And then this process will give you a new cluster tilting subcategory, which is extension closed. And our process would give you exactly the same result. And this was the result I wanted to end with. So thank you, and sorry again about the technical problems.
Thank you, Francesca. Can we all please unmute ourselves and give the speaker a round of applause? Right. Do you have any questions for the speaker?
Yes, so I wondered if I take from my Ext-projective objects some silting objects, is this then the same as silting mutation? The what was it called? The replacement procedure that you defined in the first part?
So if you start with cluster tilting, or
A silting object.
A silting object. I haven't really studied too much. Can you remind me? Silting means it's rigid, and
silting just means it generates the category as a thick category, and it has no Homs and positive degrees.
Okay.
No endomorphisms. I think it should be the same thing, but I'm not 100% sure.
Yeah, possibly, yes. Up to these extra restrictions, probably, of two Galadianas and the endomorphism rings and everything. Yeah, I guess it should coincide, probably, yes.
Okay, thanks.
Thank you. Any other questions?
Could I ask, please? I didn't really understand your example, I have to say, on the previous page. If I can say what the trouble was, what I didn't understand. First of all, it wasn't clear to me how you are defining the subcategory C. Like on the right-hand page, you have something which says C equals add blue line union green line. So I think that might be the definition of C, but it depends upon the blue line and the green line. And as on the left-hand side of it, you start off with a green. In green, you have dissecting diagonals, and you have some of those. Is the following thing, is what I'm about to say, how you define C, is it that you specify a number of diagonals, like which are the green diagonals, which should not cross? Is it correct that they should not cross? And then are the blue diagonals all possible diagonals that you can find that do not cross the green diagonals? And is that how you specify your two sets of diagonals?
Okay, so yes, you start by choosing your set of green diagonals, which are these. The only rule is that they can't cross each other. And then for these, divide your bigger polygon into cells. And then in each of these, in this case, we have 5, you either take all of the diagonals or none of them. So you're not allowed to take some of the diagonals inside. So for example, in the one on the right page, I've chosen the cells bordered by 5, 8, 9, 12, and 4 to take all of the diagonals inside. So that's how I've chosen those blue ones. And same thing for another of the cells, while I've chosen the remaining 3 cells to be empty. But yeah, of course, when you start with a set of green diagonals, you have many choices for each of the subcells, subpolygons of your polygon. You have 2 choices, taking none of the diagonals, all of them. So yeah, choosing the green diagonals doesn't.
And that is an arbitrary choice. Like you may just happen for some particular example to choose that one cell has no blue diagonals in it. It's an arbitrary choice.
It's an arbitrary choice, yeah. So any choice would give you an extension closed subcategory.
Okay. Great.
And then when I write C's add of blue and green, I just mean, well, each of the blue and green diagonals correspond to an indecomposable object. So C is add of these indecomposable objects.
Yeah, I get that. Thank you. That explains it. Thank you.
Thank you, Peter. Any other questions? David, were you about to ask something?
Yeah, I was going to ask, so you have these Ext-projectives, and you took these weak left almost Auslander-Reiten sequences. And so the reason why it couldn't be an AR sequence is because this term on the right-hand side was Ext-projective. But in the bigger triangulated category, you could take an AR sequence, right?
Yes.
And I was wondering,
you get C.
Yes.
You mean, yes.
And I was wondering, is there an easy relation, or do you know of any relation between these 2 triangles? Like how they could differ in the other 2 terms, I guess, because the first term on the right would be exactly the same.
Yeah, that's a good question, because in the other case, the one where you actually have an Auslander-Reiten triangle in your subcategory, these 2, I don't know if you've looked at this before, but these 2 triangles are very much related, because you actually just take the cover of the other end term and then you complete it to a triangle and you get the Auslander-Reiten triangle. Here, I can't remember if I looked at this at some point because this is a fairly old project. I can't remember if there is an obvious connection between the triangles. Maybe there is something, but possibly not. Maybe I should look at it again.
Okay,
Sorry.
no problem. Thank you so much. No, thank you.
You're welcome.
Thank you, David. Any other questions?
So yeah, yes, one more question. Is
please.
there any paper where I can read up the details?
Yes, there is a paper. What is it called? I think it's called Almost Split Sequences. Let me. Yes. It's called Almost Split Morphism in Subcategories of Triangulated Categories.
Okay.
And it's published in the Journal of Algebra and its Applications.
Thanks.
I can write the name. Yes, I've written the name in the chat
Perfect. Thanks.
if you're interested.
Thank you. Any other questions or comments? Well, in that case, let's thank the speaker again.
Thank you very much.
It's a good thing that you had all this written up.
Yes, I'm really glad I did. And I'm sorry, I would have added slightly more details, but yeah. I
Right,
can,
you can't-
if you're interested, I can send you the slides with more.
Yeah, please. Yeah, I'll share them with the people who are here today.
Okay, thank you.
With the people who are here today. Okay, thank you all for coming. Next week we have Liran Scholl from Charles University Prague. So yeah, I hope to see you all there. Bye-bye.
Thank you very much and see you soon.